Okay, so when you type a prompt into an AI, what actually happens to your words? You know, the common wisdom is that they get tossed into this complex digital brain, get all mashed up, and are basically lost forever. But what if that's just completely wrong? What if instead of some unknowable black box, the AI is actually a perfect mirror, holding a flawless, crystal-cleared reflection of everything you've ever told it? Let's dive in. So here's where we're headed. First, we're going to tear down this big idea we all have, the AI blender myth. Then, we'll get into a pretty surprising, lossless truth that flips everything around. We'll see how researchers prove something that seemed impossible, then watch them literally reverse the AI. And finally, we'll unpack what this all means for you and, for your data.
All right, so let's kick things off with the idea that has pretty much guided our thinking on language models for years. This deep-seated belief that once information goes in, you can never really get it back out in its original form.
Really, the best way to picture it is this blender analogy, right? You throw in your prompt, your words, your questions, maybe some code, and the AI just whirs into action. It blends all of that stuff into this abstract, kind of soupy mix of numbers. And yeah, the text it generates is something new, but the original ingredients, they seem to be gone, just totally mixed up and gone for good. And look, this isn't just some random guess. It's baked into the very design of these AI models. You look at the building blocks of a transformer, stuff like nonlinear activations, these attention mechanisms, they all feel like they're designed to throw information away. They squeeze and squash data in ways that just feel, well, irreversible. It just seemed obvious that different inputs could get mushed into the very same internal state. But a brand new, kind of groundbreaking paper is challenging this entire foundation. It's suggesting that our intuition, that whole blender idea we've been leaning on, is fundamentally wrong. And here it is, the huge shift in how we need to think about this. On the left, you've got the old blender idea. You put in hello world and maybe hi there, and they could, in theory, get mixed down into the exact same internal code. Information gets lost. But the new reality, this mirror on the right, is a whole different ballgame. Here, every single distinct input, no matter how tiny the difference, creates a perfectly unique internal state. The information isn't lost at all. It's flawlessly preserved. Now, the fancy mathematical term for this mirror property is injectivity. It's actually a pretty simple but super powerful concept. If something is injective, no two different inputs can ever produce the same output. It just means the whole process is completely lossless. The AI isn't a blender. It's a perfect encoder.
Now, okay, making a claim that big, one that just turns years of intuition on its head, that's one thing. But proving it? That's something else entirely. And the researchers here did it with an absolutely incredible amount of rigor.
They didn't just test a few examples and call it a day. Not even close. Their evidence is built on two, unshakable pillars. First, there's a formal mathematical proof that shows why this property has to exist. And second, they did a massive real-world search to see if they could find even one single exception to the rule. This visual here really helps get the core idea of the math proof across. The researchers basically showed that the chances of two different prompts creating the same internal state, what they call a collision, is a measure zero event. Think about it like this. If you just randomly toss two giant sheets of paper into a room, they're probably going to cross along a single thin line, not a whole overlapping area. That line has zero volume, right? Well, in the same way, these AI collisions are just mathematical quirks, not something you'd ever actually run into.
So even with the math saying that these collisions are pretty much impossible, the researchers went on a hunt. They set up this massive experiment, running about 5 billion comparisons to see if they could force two different prompts to create the exact same internal state. And after 5 billion tests across some of the best language models out there, how many times did they find a collision? How many times did two different prompts end up looking the same on the inside? 0. A big fat 0. Not a single one was found. And this table just hammers the point home beautifully. It shows the closest they ever got to a collision, the minimum distance between the internal states of the two most similar prompts. And as you can see, those numbers are all clearly not 0. But here's the really wild part. Look at the difference between the first layer and the final layer. The separation between prompts actually gets bigger as it goes deeper into the model. The AI isn't blending things, it's actively pulling them further apart. So if every single prompt creates a truly unique, lossless internal state. That brings up a pretty mind-bending question, right? Can we run the whole process backward? Could we take that internal state and perfectly rebuild the original prompt you typed in?
And the answer, which is just stunning, is yes. The researchers actually developed an algorithm to do exactly that. It's called SIPIT, and you can think of it as basically the unblender. It takes that jumbled soup of numbers and turns it right back into the exact original words.
So how on earth does it work? Well, it's surprisingly straightforward. First, you need to get your hands on the model's hidden internal state. Then, you just start at the beginning. You guess the first word or token, and you run it through the model. You check if the state it creates matches the target state you're holding. If it's a match, boom, you found the first word. You lock it in, move to the second spot, and just repeat the process, token by token, until the whole prompt is perfectly rebuilt. And this chart just shows you how ridiculously effective SIPIT is. You've got other methods getting 0% accuracy. A simple brute force attack can get there eventually, 100% accuracy, but it takes almost 4,000 seconds. SIPIT, though, it gets perfect, 100% accuracy in just 28 seconds. It's not just possible to reverse the AI, it's actually fast.
Okay, so this whole discovery is way, way more than just a cool computer science trick. It fundamentally changes how we have to think about AI safety, about transparency, and maybe most importantly, about the privacy of our own data.
And really, it's two sides of the same coin. The good news is huge for interpretability. Since we know no information is ever lost, we now have a real solid way to audit and understand why an AI made a certain decision. But the bad news, this is a massive red flag for privacy. It means your data, your personal info, your company secrets, anything you type in, is perfectly preserved inside the model, like a perfect invertible recording.
So what are the big takeaways here? First, any system that stores these hidden states, even for a second, for caching or whatever, is basically storing your raw text. Second, this creates a huge problem for data deletion policies, the right to be forgotten. You can delete the prompt from a log, but if that internal state exists anywhere, the prompt can be perfectly brought back. And finally, and this one is a bit chilling, there's no such thing as free privacy. Once your data goes into one of these models, it is, in a very real way, perfectly recorded.
And I think this quote from the paper itself just says it all. We used to think of these internal states as these fuzzy, complex abstractions. But we know the truth now. They are not abstractions. They are the prompt, just in disguise. Which leaves us with a final and pretty unsettling question. In a world where an AI's memory is a perfect, lossless, and now provably reversible recording of our words, what does the word delete even mean anymore? Can our data ever truly be forgotten?